Okay, good afternoon, everybody. Good afternoon, ladies and gentlemen. I would like to introduce myself. My name is Harisa, and I am the moderator here. Well, we are going to have the we are going to have Universitas Dharma International webinar series. And today we are talking about the mechatronics and its impact on agriculture. Well, I'm going to give you the ground rules for the webinar. Okay, first of all, the first one, microphone for all participants will be automatically muted during the presentation. And then please send your question or comments as a private message to account name Q&A. That's my name. You might send to me. For Zoom user, and please use comment section on YouTube. For participants who are using the YouTube, 15 minutes for question and answer. So we limit it for 15 minutes. And the third rules is about for those who are willing to ask questions or to give comments verbally, then please raise your hand and you will be unmuted by the host during the Q&A answer. And also, you will be able to provide with links that will be used for generate e-certificate via chat on YouTube. For Zoom and via comment section on YouTube. Okay, now we begin. Okay, first one, I would like to ask the opening speech from Dr. Titi Limijati, Bachelor Economic and Master Magister Management. He's going on behalf of Dr. Sofian Sugiono. Dr. Sofian couldn't be able to come because he got sick. Please welcome Dr. Titi. Welcome, Dr. Titi. Hang on. Okay, Dr. Titi, welcome.
Okay, thank you, Harisa.
Okay, thank you.
Okay, the Honorable Chief Executive Perkumpulan Buntek Bio, Mr. Witanli, Supervisor Chief Perkumpulan Buntek Bio, Mr. Udaya Sakya Halim, the Advisory Board of Buddhi Dharma University, Mr. Udaya Halim, who are in Perth, Australia today, and Rector Buddhi Dharma University, Dr. Sofia Sugyoko, Magister Management, CPMA, the admirable guest speaker of today's international webinar, Professor Jones Billingsley from University of Southern Queensland, Australia. Thank you for your time and presence in this webinar. Yeah. Thank you and welcome everyone from across Indonesia for coming to this international webinar. Representing the Rector of Buddhi Dharma University, I wish you all a good afternoon and good health. First of all, thanks God Tiratana for his blessing. We are able to gather here with our well-being to attend Mechatronics and its impact on agriculture webinar. This webinar is Buddhi Dharma University second international series with more than 1,000 registered participants. Ladies and gentlemen, agriculture is the foundation of the nation's economy. The well-developed agriculture will result in economic stability. The development of agriculture is directly proportional to the economy of a nation. A developed country is a country that can fulfill its citizens' primary needs. Mechatronics is a combination of engineering studies with mechanical engineering, control engineering, electrical engineering, and software engineering. Yeah. These studies are combined to produce a product or automation intelligent enough to work efficiently. In this webinar, Professor Billingsley will explain the optimization of automation in agriculture with help of mechanical, electrical, and software engineering. Ladies and gentlemen, this webinar is an active contribution of Buddhi Dharma University to support the development of science and technology that has been rapidly advancing to better the human life. Once again, let us big thanks to Professor Billingsley. I wish you always in good health and well-being. I give my thanks to executive, supervisor, and advisory Kumpulan Buntek Bio who always support all our activity. Thanks also to Mr. Amin Suyitno as the Dean of Science and Technology Faculty. Miss Harisa as the moderator. The entire webinar committee and attendance. You all make this webinar possible and success. Lastly, enjoy the webinar. I hope the knowledge being today is enjoy the webinar and thank you to everyone. Thank you.
Well, Dr. Titi, that was a wonderful thing. Thank you so much for your speech on behalf of Rector, Dr. Sofian Kyoko. Now, okay, we come to Mr. Udaya. Do we have to speak? Mr. Udaya, as a member of Advisory Board of University. Please welcome Mr. Udaya. You might give a speech for this. Okay, you need to unmute. Okay.
I think I hear lions in the background.
Okay, now I'm on. Thank you very much indeed. Good afternoon, ladies and gentlemen. First of all, on behalf of the advisory board of the University of Buddhi Dharma, I would like to thank Professor John Billingsley, the speaker of today's webinar, with the title Mechatronics and its Impact Agriculture. For Indonesia as a country with a population around 260 million, the fourth biggest population in the world, agriculture is indeed the backbone of the country to be able to keep the sustainable food production and supplies, not only to feed its own people, but to share with other people of other nations as well. Drones are a great example of mechatronics in practice. There are many interconnected systems that depends on multiple disciplines, communicate and functions as designed. In the last couple of years, our Indonesian Agriculture Department has been introducing the use of drones, not only to spray pesticide and fertilizer, but for other purposes as well, such as to investigate the proper growth of the crops, to inspect irrigation condition, to identify the fertility of the ground and other monitoring functions. The demand for engineers with experience and knowledge in computing, robotics, and engineering principles continues to grow along with the evolutions of industries that require AI, artificial intelligence, such as automations, robotic instrumentation, sensors, and artifacts design, control system, factory automation, software, and autonomous vehicles. Another very good example of how mechatronic engineers in the development of new technologies in car brakes, for example, where modern sensing, actuation, computing, and control technologies are integrated to make braking system more amazing and much safer than ever before. Without any further ado, I once again thank the speaker and the organizing committee who have put lots of efforts to make this webinar a success. Thank you and good afternoon.
Thank you, Mr. Udaya. That was so wonderful. Well, now we are going to begin to the webinar. But before then, I would like to say, we would like to say, to highlight participants from the overseas, from Pakistan, Malaysia, India, Egypt, and China. Thank you so much for joining us. Welcome to this. Right. We began to the speech. We give it to Professor John Billingsley. Before that, I would like to say about the short biography of Mr. Billingsley. Dr. Billingsley is professor of mechatronic engineering at the University of Southern Queensland, Australia. He is a fellow of the IIT UK, past fellow of the Engineers Australia, as well as senior member of the IEEE USA. Professor Billingsley is one of the founder Australian National Centre for Engineering in Agriculture, NECA, and NCEA, recently the name of Central for Agriculture Engineering. Professor Billingsley completed his academic degree at the University of Cambridge. He remained Cambridge as a fellow of Sydney Sussex College after he completed his doctorate degree, and 8 years later, he moved to readership at Portsmouth Polytechnic, now is Portsmouth University, and later became professor of robotics. He leads group in researching and craftsman robots and walking robots. He has found company designing embedded electronic for domestic appliances and nuclear test equipment. In 1992, Professor Billingsley moved to Toowoomba, Australia, where he applied machine vision to precision tractor guidance. This year, he was joint organizer of 26th Annual Conference on Mechatronics and Machine Vision in Practice, a series which he inaugurated in 1994. He also has numerous publications on control and theory and robotics. Well, welcome, Doctor. You might talk to me. Well, I would like to let you know that he's going to give the video, but before then, he is going to speak. Okay, welcome, Professor.
Well, you have given such a fantastic build-up. I'm feeling embarrassed. I do hope I'm not going to disappoint you. But what I have to tell you is, when I was giving a lecture online this time last night, we had a power cut.
Oh.
And that meant that I was worried we might have another one. So I spent part of this afternoon my time, but very early in the morning with you, recording a piece just in case.
Mhm.
Now, if that piece goes wrong, I'll come back on live. But in the meantime, if you would like to play that, I will sit and then I will hope to wait for a flood of questions.
Hmm.
It's the questions that really make this kind of thing worthwhile. So if you play the video, I will sit here quietly and watch with you.
Okay. Okay. You want us to play the video now, or?
Yes, please.
Okay.
Well, last night, it was last night over here, it was your afternoon, I was running a class and suddenly we had a power cut. And when you got a power cut, it's a problem because the router is out, the internet is out, you are totally on your own. So I want to be sure that we've got something for me to say to you. So I'm recording this. I'm going to be there live, power cut permitting, but let's record this as it stands. Now, what makes a robot? Well, we're not talking really robots here. We're talking about mechatronics. What's the difference? In the mind of the general public, mechatronics means a robot. But the big feature of a robot is that it moves about. They expect to see something moving. Those who follow Hollywood expect to see an actor in a tin suit. But the essence of mechatronics is the sensing. Now, I first started my love affair, if you like, with mechatronics 60 years ago when I joined a graduate apprenticeship with a company that made autopilots. If you consider a jumbo jet is the ultimate robot. It has all the computation, it has all the sensing, it can guide that plane, keep the altitude right, land it automatically, and even taxi it to the right air bridge. Well, the things we were playing with then were very, very much simpler than that. But there are still mechatronics. In those days, if you wanted to measure the bank angle of a plane, you had to use a pendulum, a little gadget with a magnetic chunk on it that would detect how far it had moved, the so-called E&I pickoff. You want to amplify the signal, so you had to use a magnetic amplifier. This was a lump of iron with a coil around it, which worked by the saturation of a mu metal coil. It's all so different now. Look, let's go back, if you'll forgive me, into a little potted history of my path through mechatronics. And at the end, I want to give you some zany ideas that could well be research topics so that you can push mechatronics on even further. And we've got to remember that we're talking about agriculture. And in agriculture, you expect your robots to move around. Well, okay, that's fine. Look, let's share screen. And I will have a whole heap of pages that aren't the one that I want, but I can work my way steadily through to pages that I do. No, I don't want those. Let's reduce that to a single chunk like that. Let us try to find the page here that I've got open, and that's got a load of pictures. So as I say, my first foray into mechatronics was in the aircraft industry, designing autopilots. And I did most of the design of a thing called SCP-7, a lightweight autopilot that was supposed to be really cheap. It ended up less cheap than that. And that was still flying around about 10 years ago. Then from there, I went back into Cambridge, and we had a research group in Cambridge, and we were looking at all sorts of things you could do with a single board computer. Now, by single board computer, I mean a thing with a whole lot of pins and wire wraps and stuff on it. We put together the acoustic telescope, which took signals from 14 microphones and worked out where the noise was coming from in Concorde. Okay, it came from the engines, but how far behind the engine did it come? Is it worth shrouding that part? And some of my Clive Sinclair, and they had a lot to do with the design of the X81. In those days, personal computer was not a word that you used professionally. Well, after a lovely time doing a lot of fruitful stuff in Cambridge, I moved off Portsmouth Polytechnic, as was. My fellows here I was at University of Don, they commiserated with me until I told them that I'd be getting twice as much money. I apologize. Look, let's go to this first picture here, and that is showing you the Puma robot that we got with a project that we called the Craftsman robot. Now, the idea with the Craftsman robot, robots mainly were shifters, things for moving things from place to place. And the idea with this was, no, you give the robot something to do things with. This was adjusting energy regulators. These things are in your electric cooker for keeping the hot plate at a sort of right temperature. They don't measure the temperature, they model the temperature. Open loop. I could go into a whole heap of control theory, but that would get boring. So let's have a look at this thing. And nowadays, of course, in the automobile industry, you've got robot arms with welding torches and not torches, electric welding equipment in left, right, and center, whole armies of them. You've got armies of them cutting up bits of meat. You've got armies of robots doing all sorts of things. So this idea is now very much old hat. And this is one of the things about research. Your brilliant discovery 1 year is old hat a couple of years later. Just look at what we're doing and say, well, not us, other people with cathode ray tubes. Who would use a cathode ray tube now? We had the LED and we had the all sorts of other techniques. The liquid crystal display. I went to a thing at the IEE where somebody was showing off the first example of a bit of liquid crystal. That went into the 7-segment displays, but now we've got television sets with 4,000 by 4,000 or so many pixels. Absolutely fantastic. So after that, what did we do? Well, I was also doing things. I set up a little company that was doing mechatronics for the domestic industry. There were those energy regulators. We were looking at fancy cooker clocks that could behave in the way that you would want them to. And somebody from that firm, he thought I was having so much fun doing research, he wanted to come and join me. So he got a 1-year Royal Society fellowship to come and join me and work on walking robots. Arthur Colley, I'm afraid he is no more. But this, we called it Robot 1, and it looks a bit like a coffin on legs, and it's pretty unsteady. It did not work ever so well, but it got us started. The innards were a whole mess of these single board computer versions of the BBC microcomputer. Do you remember that one? Fantastic in its day. And this was acting in, and let's go on, well, after a bit, we decided we were going to get the mechanics a lot better. And this is Robot 2. And Robot 2 went along to make a name for itself on television. There it is, outside of a building climbing up. I didn't mean to show it in that order. I meant to show the television version there. Look, let's minimize that. And let's go back to these things. And somewhere here, I've got Robot 2 as a bit of video.
This is Robot 2, and according to its inventor at Portsmouth Polytechnic, it's the world's first multi-limbed, insect configuration, wall climbing robot. It's going through its calibration exercises at the moment so that it knows exactly where it is and what the limits of its movements are. And in a moment, it should gallop, in a manner of speaking, actually about a meter. A main computer, which is sending those instructions up this umbilical cord here, together with compressed air to drive it. But what allows Robot to climb is a design taken directly from nature's technology, because like all natural climbers, it has a body which hangs below its knees. Pneumatic valves, the flow of compressed to pistons with microcomputers in the legs tell the robot how hard it's pressing against the surface. And once it's found a foothold, it uses suction to cling on. But if it comes across an obstruction like this, it won't put its foot down until it's found somewhere to move it to that is safe. So let's just wait. it should skirt around it and find somewhere else to go. There we are, quite clear. Now, it's this ability to test and check and to change its behavior according to environment that should one day allow Robog's descendants to undertake the risky business of climbing real buildings. And then high, inaccessible places will be washed and worked at by fearless robots with nerves of aluminium.
Well, that was fun. Let's the last one. Yeah, able with that. Thing to get the year's dose of radiation in 1 minute. Couldn't let human beings in there. But this thing that we call Nero, nuclear electric robot, could go in there and not only inspect, but chop off little bits of absolutely fantastic. Now, when we took that to the nuclear industry, they started sizing it up and working out how much it weighed. Why? Because when they'd finished with it, they'd have to dump it in a nuclear radiation dump. And that was going to cost them quite a bit of money. Okay, so let's move on and see what I've got for you next. Yeah, life in Portsmouth was really good fun. But I used to get arthritis in the winter. I used to seize up. My wife had been brought up in Kenya, and she wanted to get to warmer climates. Australia beckoned, and off we went to USQ. Now, you'll have seen the golden phoenix emblem in the flyer for this. USQ is a lovely little university, 100 miles west of Brisbane, up on the Darling Downs. It's a couple of 1,000 feet up. That means that it's not so hot and mosquito-ridden as Brisbane. It's a lovely place. And there, Sam Kubro got the bug on walking robots, and he produced a thing called a stick. He's gone off to other parts now, but there is his robot, which is now gracing the Powerhouse Museum down in Sydney. Let's come on. When I came to Portsmouth, let's say when I went to Portsmouth, there was a lot of industry around, and we could collaborate closely with industry, and that was great. But Toowoomba, that's up in agricultural country. The biggest show in town in Toowoomba was agriculture. And now I'm finally getting to the point. How is mechatronics changing the face of agriculture? And we had the idea that if you want to do chipping, that's to take like a hoe along the field and cut out all the little weeds between the rows, you have to be extremely accurate. At the time that we were doing this, GPS was coming into its own, and every farmer thought that GPS was the bee's knees, able to do everything. But he wasn't able to get the 2 centimeter accuracy or better that we needed to drive the tractor along where the plant was, not the GPS location of where you thought you'd planted it. Look, we've got another one of these somewhere. Let's show you where have I got it. I've got out of sequence, haven't I? Because before getting into that stuff, there is the smaller. That is the one I've just shown you. Sorry about that. Let's go into these two just for a bit of fun. This was a thing that we called the toad. And the toad, of course, we could let that without something on tomorrow's world.
That is head and shoulders above.
So,
It was designed by an Australian university. So that one's certainly not going to make a mess of your carpet. So let's move on up now to number 4.
so that's got out of that stuff. Let's get back onto this business of vision guidance. Look, we're up here somewhere.
Now let's get back to the mainstream of machine vision, guiding agricultural vehicles. In the mid-90s, we developed a system based on rather antiquated hardware, but it worked. The farmers swore that it worked. We put it on the market, and not enough of them bought it. For reasons I could explain at great length. I think it's because we priced it too low. Yes, not expensive, but too low.
Queensland cotton farmer Peter Richley has a new techno toy in his tractor, one which enables him to say, "Look, Mum, no hands."
That's been great. Probably the most benefit I found is how relaxing it is for you when you're driving. It's one of those jobs we've done all our lives and didn't realise that you're tense and on the ball the whole time.
No longer does Peter emerge from a 14-hour day in his tractor completely exhausted. A computer does the driving for him. It takes in images from a camera mounted on top of the tractor cabin, processes the information, then transmits instructions to the hydraulic steering, keeping the machine on the straight and narrow, more accurately than even the most skilled of drivers could.
If we're driving straight all the time, we're not knocking crop out, so therefore there's an obvious financial benefit. Plus, we can set up our cultivators to cultivate closer to the road, minimising weeds, which allows your crop to grow better.
Peter is one of 4 farmers field testing this prototype system. After only 1 season, he can't imagine life without it.
So if he can't imagine life without it, why on earth didn't more of them go out and buy them? Well, that's the snag. Look, let's go through the slides if I can find them. Oh, dash, that seems to have got closed down again. Look, I do apologize for this. I've got to go to there and to there. And now I'm back on the straight and narrow with my slides. Image 10, stick smaller. This, as I say, was the video I've just shown you. Let's go back into that one. And what have we got? Yeah, this is really just showing how antiquated and primitive the kit was that we were using then. We had to put a camcorder on the roof of the tractor. We had to grab the images into a thing used just for grabbing video for entertainment. We had a tower case computer doing all the computing. And we had that horrible little cathode ray tube going there to show the information to the driver. So what's different today? Well, let's have a look. There's that picture that you saw. We were able to put that thing into another version. I've cut off the film shorter than the fun bit. We had this belting up the field, and that was fine, but it was still primitive. So let's now go back to our, if I can find it, back to our things here. Yeah, all sorts of things there. Look, no, let's show you this other stuff first. We did a device that could train cutting horses. It had to run along and pretend to be a little calf. In a cutting contest, there's no actual cutting going on. The horse tries to separate a young calf from the other. And they train them to do it very, very well indeed. The horse does really nearly all the work and the rider's just a passenger. And that got another chunk on tomorrow's world. It's a robot of sorts that can remember where it's supposed to have gone. but that's not so much fun. And another project we got into, getting more agricultural again, was cattle for real. Now, I don't know how your agricultural, sorry, how your beef industry works over there, but in the middle of Australia, the cattle run wild. They eat what they can, they grow fat, they breed occasionally as they come to a watering hole, we check them to see how they're going. There they all are. And then we gather them together, we muster them, and we harvest them. Poor old cattle are then driven into these things, taken off to the abattoir, and that becomes great Australian beef. Well, they don't go straight to the abattoir. They usually go to a feedlot where they live the life of luxury, getting more meat on them because they'll sell for more. Agriculture is an industry where you have to be not too sentimental. Well, here is a picture of something that I want to show you in a bit more detail. We had a project to see who was coming to drink at the watering holes. Water's scarce in the middle of Australia, and we want to let the dingoes have a go. We want to, well, no, dingoes were not keen on. The kangaroos, yes, they're welcome. Cattle, of course, but wild boar, wild pigs can do a lot of damage. And we wanted a system that could corral off these wild pigs and keep them there so we would come and harvest them. There's a lot of money. Okay, then to the watering hole. We cheated a bit. We put a blue background there so the computer could look at what was blue and what was not blue. And let's now go and try and find this bit of computer software here. There one. That's the same thing, and this actually is a running program. Now there's our cow against that blue background. How do we find the border of that cow? This is a picture without a megabyte of data in it, and we want to reduce that to something that we can match against a template. We use a tracing algorithm, and that runs around here. This is much slower than it actually does it in practice. I can have a tracing of a room full of people at frame rate. And what it's doing is stepping up a bit across the boundary, and zigzagging its way along that boundary. And it's mapping all the east and northeast and southeast and so on as it goes. This is pretty heavily quantized. Looks nasty. Let's smooth it. And what that will do is to take the ants, and this picture here is reconstructed from that trace, so I can smooth it a few more times, and it still looks like the outline of a cow, but it's got 377 data points in. That's an awkward number. Let's pack it. And now I've packed that down to 256 points. I'll smooth it once again. And this now is a template. It's got a mere 256 bytes to it that you can match as a template against your templates of all known animals. And you work out who's coming to the watering hole. This is a technique that I've not seen used widely, and it could well be the focus of a bit of somebody's research. Let's close that now. And let's now go on to something else. I was showing you this wonderful antiquated work that we were doing on trying to fit two of plants. The big breakthrough in that one was that we didn't do edge tracing or any of the fancy processing that you'll find in a lot of packages and libraries. We simply said, look, we've got all these little dots there. They are data. We will fit the best straight line through those dots, but we will couple those dots into keyholes. So let's see here, this that I did earlier. And look, what I'll do, before we get started on that, I'll pause it and I'll go back to the beginning and I'll try and close this thing down again. And if you look up here, somewhere, you will see a URL, stein.com, rofit.htm. Now, if you go to that location and try running it, won't work. You've got to download it to your own machine before Windows will give you permission to access the video. So let's watch this. You'll see it soon switch to the download. And there we're looking here at the downloaded version. And you're looking at me putting up just a pattern of green blobs on a bit of paper. And you will see that that is now tracking those blobs beautifully. That will do beautifully well for guiding a vehicle along crop rows.
Well, you'll see that I changed computers because the other computer wasn't fast enough to handle the row guidance and recording at the same time. But here's a little snippet I've cut in, and you can see all these stripes across my face. This is just a web application, as you see. And you can download it from a URL that I'll give you. And that means that you can do all of the vision guidance, clever vision stuff on a smartphone. You don't have to have a big PC. You can have an Android.
Well, that was me rallying away a little while ago about that. Look, while we're at it, we ought to have a commercial break. My wife just came in to remind me that I had to be really sure that I was recording. And this picture shows that she is putting her life history up onto Amazon, and that will describe her life in Kenya and all sorts of things. There she is holding our kookaburras, and life is great. But let's now, let's just, I'm not quite, look, I'll whiz through these so that I don't get lost. Those are some of the pictures. That's a nice little thing that you might like to play with. Let's go back through these. And there I have my slide ideas for discussion. I warned you that when we came to the end of this, a heap of little ideas on you. They've been buzzing around my head for a long time, and some of them have already been done. A long time ago, I did a spoof version of the Dad and Dave stories, where I was thinking of what would happen when a little robot found its way onto a farm in Australia. Now you can pause this, and if you can go to all the trouble of typing in that huge long URL, you can find it. But if you just try Googling John Billingsley Strange Selection, you'll find that link, and it's a nice little story. And the idea in that is that you don't have to be big. The Australian robot has to be big because drivers are hard to find. But in general, the moment you can make your robot autonomous, it can be as small as you like. The thing that decrees how big it's got to be is the payload it's got to carry. Okay, it's not going to do any good cutting a corn crop or doing other harvesting things, but for going up and down the roads chipping, it's absolutely fantastic. doesn't have to be any bigger. You ride on, oh, sorry, your ride-on has to be a lot smaller. Or and this funny little story was what happened when people bought one of these second-hand and got it working. Okay, let's carry on with the idea of that little robot doing. From all go, and no, you do it at night. If it's autonomous, you can snooze on gently until it gives you a phone call to say it's got stuck, and it can then use its own lighting. What's so special about? If you want color vision, it is rotten at color vision. We can sense red, we can sense green, we can sense blue, but any color in between is as though Beethoven only had 3 notes on his piano, and he had to get the difference by hitting them or with different combinations of loudness. Light has an infinite spectrum of frequencies. Think of all the notes on your piano. You might want to try an E sharp with something else. No, E sharp is F natural. Sorry, I'm talking nonsense there, but you get the point. When you are looking for color, you want to find a way to make 2 things look different. Now, a red object looks different from a blue object because it reflects a lot more red light than it reflects blue light. To tell the difference, you've got to be able to tell the intensity of the red light and the intensity of the blue light. And you are looking at the difference between those intensities. Now, when you've got 2 different things that look the same to the human eye, but say to a bumblebee will look totally different because it can actually see perhaps into the infrared or the ultraviolet, to make them look different, you have to use 2 different wavelengths where their responses are different. And you can put a little white patch in your reflection so that you can just even out any difference in brightness, and it's the contrast between them that will tell you, oh yes, this is a weed, dig it up, or oh yes, this is a seedling, cherish it. But human eye can't see that. And cameras are built in a fairly grotty way to mimic the human eye. They have 3 color filters in them. But you can use an LED, you can use a blue LED, a red LED, an infrared LED of a very precise frequency. So here's your little robot going along at night, doing its own thing, and it gives a flash of that frequency, a flash of that one, compares the 2 pictures. Ah, I saw weed. Get rid of that weed. So here's your microspectral illumination, an area where you can do that. But let's go back to the idea of a little robot. We've now got something that you can download, and it will run in a browser in the smartphone that you abandoned last year because it wouldn't get G4 or 5, 6, whatever the latest. with it precisely down the track. As every country bungs up more satellites into orbits that have different characteristics, some are a lot nearer the Earth than the ordinary ones, they were there where it's true. More signal? More ability to take easy. Okay, couple of last little things. Look, I've run over my half hour slightly, so I'm into your question time, and I'm hoping to goodness that this is going to stir up your questions. Hydrogen for lift. A long time ago, there was the Hindenburg disaster. With this hydrogen caught fire, lots of people were killed in the flames. But you are now using things like quadrotors, these nice little UAVs, and they are doing things for investigating your crop. Or could be the cheapest chips, why are you using them if you're not? And they can be flying down the crop row looking for signs of infestation, looking for plants that aren't getting enough water. But the little rotors have to keep them aloft. They don't last very long. They're using quite a lot of electricity. Suppose you take a plastic bag, something like your refuse bag. You fill it with cheapest chips hydrogen and you suspend that balloon. You've got to make sure that the thing has got more lift than the weight of the gadget. Otherwise, it's up into the sky and you've got a job getting it back. But that can give you a great long endurance. You could be using a very simple hydrogen balloon for the lift on your UAV, on your quadrotor. Another thing I've jotted down here, steam. I had an infestation of bidens. It's known as cobbler's pigs here. They're nasty little things that grow all over the garden, and they will grow everywhere unless you keep them down. And I tried hitting it with a glyphosate thing. It loved it. It grew like mad. Steam or flame is a way of doing it. And all the people who are ecologically savvy will commend you for using steam rather than for using a chemical. It's cheap, but it's being done the wrong way. It's being done in the old steam engine way, where the big boiler full of highly compressed steam already did blow up a little squirt slit out here now. You can make that steam instantly as you put a drop of water onto something very hot. In fact, you can make that mimic an internal combustion engine. You have a cylinder which is really hot. A drop of water is injected into it, bang, it expands. That is just like an internal combustion engine, but you've got a bit of steam there that you can puff out onto the offending. No, these aren't a journal, but they're things that I hope are going to stir people up to ask questions and to debate on the way that things are being done. On that class, I had somebody who pointed out, and I had to agree very, very strongly, that if you follow the herd in your research, you're safe. You can find an examiner, you can find a supervisor. You're never going to, you can make life a little bit better, but you're never going to make that fantastic breakthrough like the one made when Ørsted saw that a compass needle twitched when he put a magnetic current near it. the really great advances in research are made by accident, by having you about you, by looking for something that isn't quite doing what you thought it should. If it does exactly what you think it should, the experiments taught you nothing. It's the experiments that go wrong which revolutionize the world. Look, I'm overrunning quite drastically now, so I'd better stop in order to give you plenty of time for questions. So I'll get rid of the screen share. And now I will hand over to the custodians of the course. And if they're still there, I hope that they will spark a couple of questions to start with. By the way, how do you like my two friends here? That's really done in my back garden. And yeah, they're there. I can also throw up another choice, and I can let you see another pair of friends there. And there are, that's why I came to Australia, as I told you before, but I did not realize it was going to be so good. Look, please, will the people running the course interrupt me and possibly stop the recording, because I want going live now for your questions, provided we've not had another power cut. Over to you.
Okay, thank you, sir. That was wonderful. The one that I like from this was is Robo Cow. So make a robot just like a cow for the agriculture. Is there any other kind of animal can be in agriculture beside cow?
A lot of toy manufacturers have made toy animals for people to love, but that's not really robotics any more than R2-D2 and C3PO were real robots. But I'm hoping somebody is going to start consisting and saying, oh no, my experiments give me the right answers, or something like that. Have you got some good questioners? I saw some people put up their hands.
Okay, I got the first question here for you. How effective is the use of smartphone for the nighttime autonomy? How to design a safe hydrogen for the lift system? And the other one is, what is your suggestion for Indonesia farmer, where technology for us is still expensive? Right, that's this question.
There's expenses and there is expensive. If you consider a while ago, a computer would cost you a lot of money. There are things like the BBC microbit. Have any of your students over there got hold of microbits?
Mm-hmm.
They're about 10 or 20 Australian dollars, which I know is expensive by your standards, but the thing has got, it's programmable, it's got an attitude sensor, a gravity sensor, and it can talk to another microbit over a sort of Bluetooth. There is nothing to stop your young researchers from getting into stuff. They do not need expensive equipment. Look, let me ask a personal question. How many mobile phones have you got?
One.
Only one?
Yeah.
Have you not got an old one that you have put in a drawer because it wasn't good enough?
The cheapest one then, Xiaomi.
Oh, well, okay, but I would guarantee that most of your students have got one or two or three.
Yes, for them, they have more than one, of course.
That's all you need. I've got quite a few here where, okay, they would log in on the 2G telephone system, but not onto the 3G. So now they're cameras. They are systems for talking to the internet. They are systems for doing anything except making a phone call. And those are virtually free. I expect that you can find a landfill somewhere near you that's got thousands of them in.
Okay.
It is a case of being adventurous and inventive.
Okay, Prof, there is one question from Mila Rosa. Hello, I want to ask, is there any significant effect for using this kind of technology on industrial and human resources?
On industrial and human what?
Human resources.
Resources.
Yeah.
Well, of course, that's what it's there for. That's what it's doing. Look, I don't like the fact that so much stuff is coming out of China, but things are coming out of China at throwaway prices. The fancy technology that used to be in my day something you saved up for months for, now find that in your supermarket for, again, I have to go into dollars, $10, $20. Okay, maybe it's 1,000, 2,000 rupiah, but that is still not an awful lot of money. And technology is getting cheaper and cheaper and cheaper because it's using technology to be made.
Yeah.
And the technology makes the stuff more automatically. Look, you no doubt have a flat screen television. How big is it? How big is it? How many inches?
Everybody have it.
I remember when you had to save up for goodness knows how long to buy one of the first 32-inch ones. Now we've got a supermarket down the street that for half that price is selling a 65-inch one. Soon the whole wall will become a television set. Technology is not just creeping up on us, it's to us like a herd of elephants. Now, I'd like to make another remark. You played the video. As I was watching it, it kept on breaking up where I was. It kept on going into that thing where the sound, instead of sounding like blah, 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 and doing that kind of noise, I do hope that what you had in your recording went out well to most people. And that means that we really did the right thing by recording it and letting you play the recording. I see that Mohammed has got his hand up.
Okay. Right. And this is the one that you haven't been answered about how effective is the use of smartphone for nighttime autonomy. Is that the question?
Oh, nighttime astronomy. Sorry, I didn't hear you properly. Obviously, the camera in a smartphone is not very good. It's not light sensitive. Look, I bought a couple of telescopes. One was a real cheapo with a long barrel, and it's got a lot more magnification than the one with a big mirror that I bought, because the big mirror is designed to get more light. If you can get your smartphone to track very nicely so that you can do, say, a 10-minute exposure, that'll do the job nicely. But I'm afraid that you're going to use something a bit better than that. But again, look, you can buy a webcam for 1,000 rupiah, no problems. And that webcam will do better than the camera in a smartphone. And if you take out the little glass filter, it's got a filter on the front that cuts out the infrared. Remove that, and then your camera can see infrared as well. There are things that you might not quite realize. Look, I'm going to vanish for a moment. I'm coming back, promise. And your camera on your computer is sensitive to infrared. So if I press a button on this, like let's press that, oh, is it not doing it? There, can you see that again? Twinkle, twinkle.
I can see that.
So that is the way that you check whether the battery is flat in your TV controller. You shine it at your computer to see if your computer can see the little light come on.
Okay.
There is a huge amount of optics, which is so simple, but which has to be understood. Multispectral vision, the fact that the eye cannot see colors very well except the red, green, blue. Okay, the rainbow is not just 7 colors, it's 1 million colors, but your eye can't tell the difference.
Okay.
Sorry, you were saying?
Okay, this is a lot of questions. I hope we have enough time then. And then this is from Christopher Kurniawan. Hello, sir. I would like to ask your personal opinion about how crucial robot is for the future.
How could it?
How crucial? How dangerous, I think.
Oh, how dangerous.
Yeah, for the future.
Yeah, robots are dangerous. TV sets are dangerous. That people get glued to them instead of doing the things, the exercise they should do. No, robot safety is important, which is once again, look, I wrote these stories for the ABC way back in the year 2000, and they were good fun. And if you go to that reference, you'll see the bit about the ARF, the Autonomous Robot Farmhand. The whole point of that story was the idea that a big autonomous robot had plowed into a housing estate. If you have great big autonomous robots, they can be dangerous. If you've got something that's no bigger than a quad bike, you can put a little panel on it, you kick it, it dies, and it is then safe. A lot of little robots can be cheaper, can be more reliable. 1, 2, 3 can fail, and you've still got a few still working, whereas you've got one big tractor fails, your farm is dead. And so this is the thing that I'm trying to get people to go for. The idea that you have little robots working autonomously, especially at nighttime. And in that way, they're safe, they're cheap, they're easy, and with the intelligence that's in a smartphone, you can make them absolutely brilliant.
Okay, right. This is from Marata Sinada. Hello, Prof. John Billingsley. Excuse me, I want to ask you about the existence mechatronics in changing human resources for agriculture aspect for the next generation in the future. What kind of solution in handling it?
The only limitation to what you can do is your imagination. If you can imagine something to do with this, you can probably do it. But it's getting that imagination, realizing what are the important things to do. With the advances in science, I don't know if you are a keen science fiction reader. Many years ago, I used to read lots of science fiction, and an awful lot of the ideas that were there, they're here now. You know, you have the ray gun. Okay, that's the laser. You have all of these wonderful things. One of the things that the Star Trek series got right was their communicator. Their little flip-up communicator was just like a mobile phone. So people will tend to go in the direction of their imagination. Now, one science fiction writer is called Philip Jose Farmer. Strange name, but he wrote about robots in farming, and he made it look a nightmare with places smothered with chemicals that humans could not go. It's not going to be like that. But the robots are going to help enormously. Look, would you like another really zany idea? There's a lot of work going on at the moment into robot fruit picking. How do you let a robot recognize when a fruit is ripe to be picked? And robots at the moment are finding that very difficult indeed. Now, we have retirement homes over here. You imagine a retirement home with a great big TV screen there, showing the view from a little robot gadget driving through the field. And there with the wonderful 4G, 5G communication, they can be using those robot arms as telekeers, doing the picking in the commands that are coming from people who are retired. But maybe you've got plenty of people, and you've got plenty of people who want to do things. In Australia, we have problems with getting people to work on the land. We have to bring them in from the Pacific Islands to do the picking. It's a case that it is worth making a tractor very big because you want that one driver to cover as much field as possible. But if you've got plenty of drivers, maybe you haven't got the same imperative. I don't know. Maybe I've got off the point.
Okay, right. Here another one. How can industrial 4.0 be applied to Indonesian agriculture? Meanwhile, the average Indonesian farmer have not mastered in internet in using technology. It means.
I'm sorry, I didn't catch that very well.
I think most of Indonesian farmer doesn't how to use the technology, even though the technology.
How many of your houses have internet connections?
Here?
Yeah.
Yeah. Now I think everybody have it because the school have to be in the house. So we have distant learning. So we use that one, internet. But
so once you have your internet connection, you have no excuse not getting in there into the software, have fun learning how robot devices, things of this sort. I don't know if I didn't catch the question properly.
Yeah, it's kind of difficult to understand either. Okay, this is M.Pd, sir. Would you like to ask question? You raise your hand. Please ask question. This one, yeah. I unmute you. Can you please unmute? Yeah, he's raising question. Please, where is it? Okay. And Novi Octavianito, M.Hd, would you like to ask question? Yeah. Okay, go ahead. If you want to ask question, you might go. You already raised your hand. No, okay. Novi Octaviani, would you like to ask question? You already raise your hand. Would you like to do that? We unmute you if you do.
I can hear a little voice in the background, but nothing here.
Yeah. It's okay. You may ask question. If you have difficulty, I might explain to Professor about that. Okay. Okay. We other thing that I'm going to say. Prof, my name is Agus Baharudin, and I have question regarding to your speech. If I want to apply this technology to agriculture sector, what would you be first thing to be done? Because I think most people do not know what to do with the first stage. Thank you.
Okay, I was talking about these little BBC microbits, cards that you can program. Sorry, somebody else got in there. You can look at the programming side, but if you want to play robots, you've got to make something move. You've got to learn how to connect your thinking device, your card, your smartphone, to a device that can drive a motor. And getting that driving the motor is at the heart of mechatronics, or at least at the heart of robotics. Did that answer the question, or have I gone off at another tangent? You've gone quiet now.
Okay, yes, I think so, because it's been some of the word. Okay, this is from Samuel Pen. Okay, hello, Professor and Moderator. My name is Samuel. I would like to ask questions. So the learning are gonna be very important on mechatronic now later on the future. So it means that how mechatronic later in the future is very important.
You've gone quiet again. I think you've muted yourself as well as muting others.
How important mechatronic in the future?
Obviously, mechatronics is vital in the same way that the small motor is vital. Go into your kitchen, you have a food mixer with a motor in it. You want to do the cleaning, you have a vacuum cleaner with a motor in it. You want an aircon on the wall, it's got a motor in it. And in the same way that we become so dependent on motors, we are just as dependent now, or becoming just as dependent on that little bit of intelligence of a built-in microcomputer. I see you are muted again.
No, because there is a sound back in my place. Okay, another one here is again, yeah. If all job can be replaced by robot, will it make human do not have any work? It's very...
Well, I'm sure that you're all so sad that your job of doing the washing up is being taken over by a big square box under the kitchen, assuming you have dishwashing machines. They're all over Australia. Maybe they're not quite so common there. There are lots and lots of jobs that I don't want to do. And you can get the robots to do those jobs. Now, you look back at ancient Rome and even at the early days of the 1800s, and people used slaves. Well, our slaves are now little electronic slaves. They are our workers who are doing the jobs that we don't want to do. But if there's a job that we do want to do, heck, we're not going to let a robot do it. That's my thinking anyway.
Yeah. Okay. I think that's any other question who wants to raise hand? Novi, you still want to ask question? Novi Octaviani. She has been, okay. Go ahead, Novi. Where are you? Are you going to? It's been raised.
I think a lot of people are thinking that it is getting late in the afternoon and they want their cup of tea.
Okay. Is that? Well, I think it's already 3 o'clock, 10 past 3. Thank you so much, sir, for the webinar today. It's been wonderful. I get a lot of knowledge for this one. For the last, I would like to ask the Dean of Faculty of Science and Technology, Dr. Admin Suyitno, to give a speech. Please welcome.
Okay, thank you very much, Mrs. Moderator. Dear participants, good afternoon. I would like to say thank you very much for attending our webinar, as well as attending. We know that our guests come from several countries, Pakistan, Malaysia, Egypt, India, and also China. We really appreciate all of you. Hopefully this topic and material presented by Professor John Billingsley can inspire of all of us and enable us to create something concrete that is beneficial to our environment. Currently, the Faculty of Science and Technology of Buddhi University has decided to hold this kind of event periodically and continuously. Has decided to also will try to propose the advance of the latest topic in technology. So please regularly check our announcement on our website and don't be miss our next event. We also thank you. We also have to say many thanks to Professor John Billingsley, who provide us with a very useful presentation and great material for us. So on behalf of our institution, I have to appreciate your contribution to this international webinar, and hopefully our relationship will be continue in the future. Thank you.
I have to thank you for giving me a wonderful audience. It's fun. I enjoy it. It's superb. Thank you very much.
Yeah. Okay, thank you, Prof. Thank you, really, thank you.
All right. Thank you so much to all participants. Thank you, Prof. John Billingsley. Thank you, Dr. Titi. Thank you, Sir Udaya. Thank you, Dr. Amin, for the webinar. We are happy to have you. Thank you all the committees, Dr. Detan, PhD. I'm happy to be here as the moderator. Thank you all for the webinar today, and we hope we'll see you again in the future. Thank you all.